of our department. She will present her work on the topic understanding supermassive black hole binaries through continuous Nanohertz gravitational wave. Please welcome on to the round show. Good afternoon, my professors and my dear friends. Today I am presenting my internship work carried out at EIF at Mumbai under the supervisory guidance of Dr. Shruti. So, my project title is Understanding Supermassive Black Hole Binaries, which are also called SMBHBs, to continuous Nanohertz gravitational. So, my main object of my project was to understand how gravitational waves from supermassive black hole binaries can be modeled in the nanohertz frequency regime, and how population of such binaries can be combined into a stochastic gravitational wave pattern. So to be more precise, I work connecting two problems. That is, I modeled gravitational waves from an individual supermassive black hole binaries, and then I generated a realistic synthetic population of supermassive black hole binaries, and using the combined result of such binaries, I generated the stochastic gravitational-wave background and studied it. So, now before beginning into describing the supermassive black hole binaries, let me briefly introduce what is gravitational waves. So, according to general relativity, gravity is not described as any conventional force. It is rather understood in terms of curvature of space. Now, what do we exactly mean by space-time? So we can think of it as a structure that combines the space and time throughout the universe. And massive objects such as binary black holes and stars can distort the space-time error. So now, when this massive and compact object can undergo motion and acceleration motion, particularly when the mass distribution of the system changes with time, which produces disturbances in the curvature of space, right? And these disturbances propagate throughout the space, throughout the space time or the universe in the form of gravitational. Now, to make it more clear, let us imagine dropping a stone in a pond. So when the stone hits the water, it creates disturbances at that point, and then and the ripples in the water propagate outward, right, from that source. So in somewhat similar manner, we can say when the changing gravitational field, from the changing gravitational field, the disturbance is created in the curvature of space-time or universe space-time, and the ripples travel in the curvature of space-time and is called the gravitational field. So now, one interesting fact is that these waves can travel enormous large distance through the universe, and they travel at the speed of light. But however, when the gravitational wave reaches Earth, the effective result on the space-time becomes very small. That is, the gravitational wave becomes too weak. So we need or we require spatial, extremely sensitive observational techniques to detect such waves or signals. So now, one more important thing is that not all gravitational wave producing sources produces the waves at the same frequency, such as so all the astrophysical sources have evolved in very different time scales, and therefore they produce the gravitational waves in different frequency ranges. So for different sources, we require different types of detectors to give different frequency ranges. For example, stellar mass black holes and neutron star binaries, they have evolving and merging times comparatively very short, typically from seconds to minutes. So their gravitational waves produced by them are a frequency of tens of hertz to thousands of hertz. And these times is particularly accessible to ground-based detectors such as light. But on the other hand, supermassive black hole binaries, these are enormously massive systems. So, and they have orbital period or orbital evolution very slow. So their time scale can range to years to even much longer. So the frequency of the gravitational wave produced by such binary systems are of the order of few nanohertz, the frequency calls the nanohertz frequency range. So to detect such waves, we generally use Pulsar Timing Array, also called as PTA, instead of using interferometer time. So what happens? The basic idea of PTA is it uses millisecond pulsars and highly precise cosmic clocks. So what happens that millisecond pulsars emit pulses remarkably at regular time intervals, and when gravitational wave passes between a pulse and the Earth, travels the space between a pulse and the Earth, it slightly perturbs the curvature of space-time, and thus it produces this slight shift in the arrival of the pulse arriving time. Okay, so the observed arrival time of the pulse gets changed. So it can delay or it can get advanced. So it depends on the flight shifting of the signal. So now, if we monitor such many milliseconds pulsars over a many long year, we can try to find the correlated variations of the time arrivals of pulses, and then we can search for the nanohertz gravitational. So here in this tabular form, I compared the frequency ranges of the different detectors. Now, coming to the main point. So let's imagine two galaxies going under merger. So when from each so at the center of each galaxy, they may have supermassive black holes. So when after the galaxy merges, these two black holes can eventually form a binary system and they start orbiting each other. So these are what we are calling the supermassive black hole systems. So when as they orbit, they emit gravitational waves and start losing energy and the angular momentum. So these energies, as a result, as they lose energy or emits gravitational wave, the orbital separation starts decreasing and the orbital frequency increases, and therefore the gravitational wave that we produce also the frequency also increases. Now here in this plot, I have plotted the two polarizations, that is H plus and H cross of the gravitational wave. And here, if we observe the binary system from an earthly inspired to coalescence, now what do I mean by coalescence? The point at which the two binaries collide or merge together is what we have called the coalescence. So when we observe it, we can see that far away from coalescence, the binary evolution is very slow. So the frequency and amplitude change is also very gradual. So it's very gradually slow. So but as the binary approaches the coalescence, the evolution becomes much faster, and so the amplitude and the frequency also increases significantly. So we can see the two polarization as the binary approaches the coalescence strongly increases. But however, if the supermassive black hole binary is observed in a PPA band, the situation is quite different. So here I have zoomed into a 30-year observation duration. So now we can see the sinusoidal wave is very constant. It has a very constant amplitude and frequency. It is not increasing rapidly like the previous picture, right? So here what is happening is the as because the binaries have an orbital evolution very slow, so the if when we observe it for a few years, such as 30 years, and finite observational time, the change is very slow. So it is hardly changes. It can approximately constant, and we do the software is sinusoidal. And so this is what makes it possible for the previous to detect such binary systems over the decades. So now, from here we can see that if now this was what we observe the gravitational waveform in the time zone. Now, what happens if we go to the frequency space? So here I calculated the fast Fourier transform for the we call FFT and transform and using the basic Fourier transform formula and transform it to the frequency domain. And we observe how the waveform signal is spread through all the frequencies. So here we can see the four panels and the high peak or the peaks that we are observing is around the frequency that are injected in the simulation. So here we will observe that as we increase the observational time, that is from 20 years to 30 years to 50 years or 100 years, the peaks gets much more narrower and stable. So as you see that for 20 years, the peak is much broader and it's not that much steep. But for 30 years, it improves and it becomes a narrower steep. So like waves, the 50 years gets also much more bigger. So what we can interpret that from this, we can say that the frequency resolution improves as we increase our observational time. So what happens is we cannot observe the waveform from minus infinity to plus infinity, right? During the Fourier transform, we took the integration from minus infinity to plus infinity. But here we observe the waveform at a finite window of time, and we will multiply it by a significant number. So by that, what is happening is the spectral broadening is getting there, or this is there, or we can say that leakage is there around the two figures. So if we increase our observation time, so we can improve our frequency resolution and thus we can improve our ability to resolve the source frequency. Now, still what we are modeling the single gravitational supermassive black hole binary. But in PK band, we are expected to have contribution from a large population of binaries, right? So as universe contains a large number of supermassive black hole binary systems. So the problem is that astrophysical quantities such as masses, frequencies, or mass ratios or redshifts, they are not uniformly distributed. They follow some probability distribution. So to match this, to match such probability distribution, I use the technique inverse transform sample. So let's say we have a desired probability distribution function Px. So what we do is first we normalize the px, then we compute the cumulative distribution function. Let's call it fx, and then we choose the random number between 0 and 1, and then we solve for x that satisfies the equation that x equals to the random number chosen we chosen. So for that, the resultant x follows our desired probability distribution, and thus the sample is the desired result. So why we are doing this? So instead of choosing randomly the masses and frequencies, which will not represent the astrophysical population, we chose to do the sample at a physically motivated distributors. Now, the first parameter that I sampled is the mass. So I started with stellar mass and of the first galaxy, which was modeled using a vector type distribution. Then the mass which I chose is from 10 to the power 11, 10 to the power 12 solar masses. And then I converted this stellar mass into black hole mass using the linear scale relation that is shown in the slide. Then and the result and it gives the realistic probability distribution. So here we can see that most of the finite systems falls in the mass rate 10 to the power 8.5 to 10 to the power 8.8, and the massive one being very rare. So here we get our desired sample. Then we require the mass ratio. So I sampled it logarithmically from uniform distribution and chose the range from -2 to 0, and its corresponding value becomes 0.0121. Now, next, I will be sampling the gravitational wave frequency. So here we are interested in the nanohertz frequency as observed by the Pulsar Timing Array PTA. So I chose the frequency range from 10 to the minus 9, 10 to the minus 8, that is the order of nanohertz frequency range. And the frequency was sampled using a power law, and the alpha value is taken as -8/3, meaning that most of the binaries spend more time at the lower frequency. So here we can see from the histogram that most of the frequencies lie in the -8.6 or in the nanohertz region, right? Exactly where the Pulsar Timing Arrays are sensitive. Now we will sample the redshift. So why redshift is important? Because it gives information about the distance of sources and at what cosmic time we are observing. So the probability density function used for redshift is given as follows, where the dV represents the co-moving volume element, and alpha is taken to be 0, assuming that constant co-moving number density, that is, no evolution is considered in the source population with redshift. So the redshift rate was taken from 0 to 2, and we can see that most of the binary systems fall in the intermediate, that is from 0.5 to 1.75. So now comes the main part, that is the stochastic gravitational-wave background, right? So still part we have done we have modeled gravitational wave of the individual stochastic gravitational so the supermassive that's a binary, individual supermassive that's a binary, but in our universe it is expected to have a much longer population, much larger population of such binaries distributed throughout the universe, right? So most of them are too big or too distant from us to resolve individually. So the gravitational wave produced from such systems, unresolved binaries, combined overlap and gives us a combined signal, which we are calling the stochastic gravitational-wave background. So here the incoherent term is very important because we are not just simply adding the waveforms at same phase, because different sources are at different positions, different orientations, they have different frequencies and phases. So when we combine this result, so we get a stochastic gravitational-wave background. Now, so what we are doing here is we compute the energy spectrum of each binary using the top equation shown in the slide. So then we convert it into the energy density spectrum contributed by the individual binary and represent it as omega GWI. And then total background is obtained by summing over all the binaries. So if we assume purely gravitational wave remains considered binary system, then the SGWB, that is Stochastic Gravitational-Wave Background, is expected to follow up if we did not by 3 power. Now we simplify our diagram. So for this, that I created a synthetic catalog containing 5 in 10 to the power 5, that is 500,000 Supermassive diagonal binaries. And each binaries had the physically motivated mass index frequency and redshift using the inverse transform sampling that I mentioned earlier. So now then I created 10 independent realizations, each having randomly sampled binaries containing 50,000 binaries. So now we can see that in this plot that the 10 independent realizations were plotted. The total SGWB, that is the total omega because of 10 independent realizations are plotted here. So in this plot we can see that there is a rising trend, right? So it is consistent with our electrical probability power law, and we also see some jagged and irregular fluctuations of features over the curve. So these fluctuations are not because of some random noise or not necessarily from random noise or numerical errors, but it is due to some finite sampling. What do we mean by finite sampling? Because we use some finite numbers of population, finite number of population in our sample. So the fluctuation differs and we call it a sample variance. So not every curve is identical for the 10 independent realization, and thus we get a different curve for each realization. And then we also might see that there are some powerful or strong spikes at certain frequencies. These are results of some individually large bright supermassive data binaries. Now these are what type of binaries? They might be very massive or they might be very near to us. So their effect or their contribution to the background is much more large, much more stronger than the rest of the population. And thus we observe a large size over the overall curve, that is the fluctuations. So now why this is relevant? Because in PTA signals, when you observe the signals in PTA, so the real gravitational signals are not smooth, right? So it may contain information about the population of the binary systems. So if we can understand the variance, then we will be able to understand or solve in interpreting the stochastic signals. So with this, I come to my conclusion that so what I did summarize in 3 stages that I first modeled the gravitational wave signals from an individual stochastic gravitational wave background. Then I generated 2 polarization, that is H plus and H cross, and studied in the time domain. Then I used FFT, computed FFT and transformed it into the frequency domain. And then we observe that if we increase the observational duration, then we can improve our frequency resolution, and thus improve our ability to resolve the source frequency. Then I created a realistic supermassive black hole population and using sampled masses, frequencies, redshift, using the inverse transform sampling, and then then I computed the energy spectrum of each individual binary and added them to form the stochastic gravitational-wave background. And the plot, though we see fluctuations in that plot due to the finite discrete population and right individual sources, it still followed the expected electrical probability power. So, presentation. The main takeaway is that using Nanohertz gravitational wave astronomy, it gives us a way to study the populations of supermassive black hole binaries, and through stochastic background, we can learn about the population of the supermassive black hole and learn their cosmic value. Thank you.
So I have a question regarding methodology. That you said that you are analyzing the signals over a finite probability, like 20 years or 100 years. So how do you handle the probability of data available together? Using what windows or what like combination of numbers.
I'm not getting it. So, what are you saying?
So then we have different types of windows for propagation. Because first, if we don't propagate, then it will cause a lot of spectral decay on both the ends, right? That will not be useful. So we have to use something like windows or
The NFT. So I used already made code, and then I injected my desired frequency into that, and that gave me the waveform that I showed. So there was no such thing as propagating the there was not a use.
Can we use them when we will do
Yes, there is an NFT code. We can use that for the yes.
like before that investments like yes. What is your second?
Rosie, I'm not sure now right now. It might be density, something related to density. I have not gone through this, I have not studied the terms that much clearly. I have forgotten. I will let you know later.
So you got problem from somewhere.
Yeah, I use my references, my supervisors or my PhD helpers help me out with that. And I have used the formula from these references. They have their own paper released. And now speaker for the SMBHB and for